guys, welcome back to Wong Chemistry channel. For this video is the part 5 of your 4.3. So in this part of video, we are going to discuss both of the hybridization process and the orbital overlapping when the central atom having lone pair. So in the previous video, we have discussed what is about hybridization process, what is about orbital overlapping for the central atom without lone pair. So for this video, we'll talk about both of the hybridization process and the orbital overlapping when the central atom right now having lone pair. So when the central atom having lone pair, what would happen to the hybridization process? What would change in the orbital overlapping? Let's see. And of course, before we start, you must definitely know the hybridization of the central atom according to the following steps. So as always, your step 1 is definitely to determine the Lewis structure so that you can determine the electron domain of the central atom by using sigma plus lone pair. Bear that in mind, we only check out for the central atom. And of course, from there, you can determine the type of hybridization of your central atom. And this is the summary of your electron domain and hybridized orbital. With the respective electron domain, you can know the hybridized orbital and the correct geometry. Okay? Bear that in mind, SP means you will have one orbital from the S, one from the P. SP2 means you will have one from the S, two from the P. SP3 over there means you will have one orbital from the S and three orbital from the P. SP3D, as you know, one from the S, three from the P, and one from the D. And of course, last but not least, when the hybridized orbital is SP3D2, it means one from the S, three from the P, and two from the D orbital. I hope you remember that. And your SP hybridized orbital that holding linear shape, your linear should look something like this. Your trigonal planar, how should your trigonal planar look like? You should be extremely good at drawing this already at this moment. Your tetrahedral should look something like this. You should know how your tetrahedral look like, and you can definitely draw it at this moment. Your trigonal bipyramidal shall look something like this. Alright, that is your trigonal bipyramidal. Your octahedral, last and not least, you know that your octahedral should look something like this. Alright, because we have been through all the hybridization process and also the orbital overlapping. Okay, so right now we are going through everything again for the compound that having central atom with lone pair. Okay, so let's look at the hybridization process when you have the central atom with lone pair. So let's look at the step 1. So the step 1 remain the same. We are still going to draw the orbital diagram for the valence electron of the central atom. Okay. Step 2 look like something different over there. Did you realize? Your step 2 is you are going to excite the electron, if it's needed, to a higher energy orbital that we call excited state. So we have come across excited state already before this. But if you are having lone pair in your central atom, they will be slightly different in your excited state, where in your excited state, you must already have the pair out electron. So, number of pair up electron will be equals to the number of lone pair. If you have one lone pair at the central atom in your Lewis structure, then you must have one paired electron in your excited state. The same thing applies to your step 3. Look at your step 3. Your new hybridized orbital form, which is your hybrid state, must also having the paired electron. The same thing. The number of paired electron that you have must be equal to the number of lone pair at central atom. So if your central atom having one lone pair, then you must have one pair out electron. If your central atom having two lone pair, then you must have two paired out electron. Okay? So for example, if I'm having a sp3, so my sp3 hybridized orbital shall look something like this. And in this sp3 central atom, let's say my central atom having one lone pair. If I'm having one lone pair, which means in this sp3 hybridized orbital, I shall have one pair up electron and another three single electron. from this is actually the lone pair. This is the sigma bond. Can you see that? Alright, so if you're having a lone pair at your central atom, it means that you need to have pair up electron in your hybridized orbital. Alright, so let's say if I'm having over here sp3d. So if this is my hybridized sp3d, okay, and let's say my sp3d looks something like this. Okay, what is this hybridized orbital stand for? It means you will have one lone pair, two lone pair, three lone pair, one sigma, two sigma. So your sp3d hybridized orbital for this particular condition means that your central atom having three lone pair and your central atom only holding two sigma bond. Can you see that? So the pair up electron over here in your hybridized orbital represent lone pair. Makes sense? So I hope you can see what makes it different in this hybridization process when your central atom holding lone pair. Okay? And of course, your hybridization process will then end with your terminal atom ground state, where you are going to draw the orbital diagram of the valence electron for your terminal atom. That is your terminal atom ground state. Okay? So don't worry if you don't understand now. We will go through a few examples at the end of this video, so you can check it out to ensure you understand more. Next, so what would happen to the steps of orbital overlapping when you are having lone pair at your central atom? So when you have lone pair, the step 1 over here is still the same. Identify the hybridized orbital of your central atom from the Lewis structure, standard. Draw the correct Lewis structure, calculate your electron domain, then you can determine the hybridized orbital. Your step 2, we are going to identify the geometry. As always, you need to know whether it's a linear, whether it's an octahedral, whether it's a trigonal planar, and so on. So make sure you can draw them and also label your geometry of your hybridized orbital. But before you overlap with the terminal atom, we have extra one step, which is in your third step. After you draw the geometry of your central atom, you need to identify and position the lone pair. So the first thing after you draw the geometry of your central atom, you need to locate and identify the position of your lone pair. Do not draw the overlapping first. You must put down your lone pair in the correct position before you move into the overlapping with the terminal atom. Okay? Alright? So don't worry, I will tell you the position of the lone pair that you can put in every geometry of every hybridization. So let's go for the position of the lone pair before we go for the orbital overlapping as everything. Okay? So first and foremost, starting off with your sp2, knowing that your sp2 is a trigonal planar. Your trigonal planar should look something like this. So what happened to your trigonal planar when you have one lone pair? So when you have one lone pair at your central atom of trigonal planar, where should the lone pair located? The lone pair can be at any of this orbital, alright? Any of the lobe. Why any of the lobes? Simple, because each and every one of them right now is in the 120 degree. So when each and every one of them is the same angle different, therefore your lone pair can be at any of the lobe. And the way that to put in the lone pair is two single electron pair out in the opposite direction. That is what we call lone pair. Without overlapping, you already have a pair of electrons. That is your lone pair. And for your sp2 hybridized, which is a trigonal planar, the lone pair can be positioned at any of the lobes. Okay? Next, we have sp3 hybridized orbital. sp3 hybridized orbital is a tetrahedral. And we have two conditions. One, your sp3 can have one lone pair at the central atom, or it can have two lone pairs at the central atom. Let's see the shape of tetrahedral first. So that is how your tetrahedral look like, your sp3. Okay? And since right now we only have one lone pair, and because the angle over here is all the same, the bond angle over here will be 109.5. Since all the angle is the same, the one lone pair can be located in any of the lones. Okay? So you can just simply put in a pair of electrons without overlapping. You already have a pair of electrons in opposite spin. That is your lone pair. Okay? Simple. That's it. That is how we determine the position of lone pair. And what happens when you have two lone pairs? When you have two lone pairs in your tetrahedral, the same reason, the bond angle are the same. Since the bond angle are the same between them, therefore, the two lone pair can be placed in any of the lobes. So same thing, any two lobes can be holding the lone pair. So let's say my lone pair is located in here, one, the first pair, and then the second pair. Bear that in mind, lone pair means you already have a pair of electron without even overlapping. Okay, you already have a pair of electron even without overlapping. Okay, that is your lone pair. And that is the position of lone pair for tetrahedral when you are having one lone pair and when you are having two lone pair. Okay? Next, when you have sp3d, you have your trigonal bipyramidal. And in this trigonal bipyramidal, we have three conditions. We have a condition where you only have one lone pair. You have a condition where you only have two lone pair. And you have a condition of three lone pair. Okay? So, first and foremost, when you have one lone pair, where would your lone pair located? Simple. I want you to look at this trigonal pyramidal. You know that in your trigonal pyramidal, you have 180 degree. Okay, that is your 180 degree. And you have a triangle over here. You have a trigonal planar over here. Can you see that? So your lone pair in this case can be placed into any lobes in the trigonal planar position. Okay, can you see the trigonal planar over here? So, your lone pair can be placed into any of these three lobes. Okay, so let's say if I put my lone pair over here. So, one lone pair, that is my one lone pair. Alright, I hope you can see what is left. You are left with your seesaw. Can you see the seesaw? Alright, you're left with your seesaw. Can you see that? So that is the seesaw shape. Okay, that is the geometry of seesaw. That's why your lone pair must be located over here. Okay? Next, what happens when you have two lone pair? Same thing, look at your trigonal bipyramidal. In the trigonal bipyramidal, you have the 180 degree. Okay, you have the 180 degree over here straight. You have another three lobe that is actually a trigonal planar. Can you see that? And when you have two lone pair, guys, means two lone pair can put into two lobes. And the two lobes is any of the trigonal planar. So you can put into any one of the triangle over here. So this triangle, and this triangle. So which two that I'm going to put in my lone pair with? I will choose this two. Alright, I will choose to put my lone pair in this two. Why do I put in that two? Because after you put lone pair over there, can you see what is the geometry that left? The geometry that left right now is a T shape. Can you look at the T shape? That is the same reason on why your lone pair is located there. The same reason as your VSEPR theory. Your lone pair must be located over here so that we can minimize the electron pair repulsion. We want to minimize the repulsion between the lone pair. That's why we are going to put it at the furthest away distance. The furthest away distance over here is your 120 degree between your triangle. So when you put the two lone pair over here, you will then produce your T shape in your Westphal theory, in your VSEPR theory previously. Same reason. Okay? Next, and the last but not least, what happens when I have three lone pair? So, the same thing, you are having your 180 degree over here. you're having your triangle over here for your trigonal bipyramidal. And since it's a 3 lone pair into all 3 of this trigonal. Okay, so the 3 lone pair will be definitely going into all these 3 trigonal shape. So the first lone pair, the second lone pair, and the third lone pair. The same reason why we are putting your 3 lone pair into this position, to minimum the electron repulsion. Okay, and from that you can see that you have your linear. Remember, from your trigonal bipyramidal we can get your linear because your trigonal bipyramidal having 3 lone pair. So this is one of the shape that is very important to position your lone pair correctly. So bear that in mind, in your trigonal bipyramidal over here, the lone pair that you can put in is only into this trigonal geometry. Okay, because of the minimum of electron repulsion. So be very careful with your trigonal bipyramidal when they are holding lone pair. The position of the lone pair must be 100% correct. Okay, before you can draw the orbital overlapping. Next and last but not least, of course, our sp3d2 that having the shape of octahedral. So what happens when you have the octahedral holding 1 lone pair? So in this octahedral, since all the bonds are 90 degrees, okay, all the angle over here is 90 degrees, they are all the same. Therefore, the first lone pair can be put into any of the lone. So let's say I put my first lone pair over here. Okay, and I hope you can see what geometry is then formed. You have this, you have this, alright, you have this, except the lone pair. What is that? Do you remember from your octahedral, when your octahedral holding 1 lone pair, that is your square pyramidal. I hope you remember that in your 4.2. Okay, that is your square pyramidal. That's why your first lone pair, the first lone pair that you have in your octahedral, can be placed in anywhere. Okay, what happens when you have 2 lone pair? When you have 2 lone pair in your octahedral, the condition is only 1. Okay, the first lone pair can be in any lone. The second lone pair must be opposite of the first. Okay, opposite of the first lone pair. So let's say if my first lone pair located here just now, if I'm having 2 lone pair, so the second lone pair must be the one in opposite direction. See that? So the first lone pair can be in any position, but the second lone pair must be the one opposite the first lone pair. As simple as that. And you can see what geometry is left behind when your octahedral holding 2 lone pair. When your octahedral holding 2 lone pair, guys, there will be 1 geometry left, which is your square planar. See that? That is the reason why the position of your lone pair is extremely important before overlapping. So whenever you are having a central atom with a lone pair, make sure you draw the hybridized orbital of the central atom and then put in your lone pair before doing the overlapping for the formation of sigma or pi bond. Okay, simple, easy. So we are going to discuss a few examples. The first one for this video is your ammonia, one of the simplest structure. Okay, as always, we are going to start off with your total valence electron, Lewis structure, and all the way down to the type of hybridization. So we are done with your Lewis structure. Then we move on to your electron domain. From the electron domain that you determine, you can work out the hybridization. So from the hybridization that we have identified, which is sp3 over here, you can know the molecular geometry. Okay, since this video is about hybridization process and also orbital overlapping, so let's go for the hybridization process first. So as always, the hybridization process will start with the nitrogen central atom, ground state. knowing that the valence electron of nitrogen located in 2s2 and 2p3. Next, since we are looking for the hybridization of nitrogen is sp3 only, and knowing that your n equals to 2 over here, we're not having any d orbital. So since we are not having any d orbital, do we need to do any changes in your excited state? We realize that your 2p is already full with your single unpaired electron, which is obviously that is your sigma. Looking at your Lewis structure, we know that in your Lewis structure, your nitrogen having one lone pair, right? So the lone pair means you need pair up electron already. Can you see the pair up electron over here? So we are not going to break the pair up electron because that will become my lone pair. In the other words, for this case, your nitrogen excited state will have no changes. And guys, even though there is no changes, you still need to draw your excited state. There is no changes in terms of the electron arrangement, but there is actually changes in terms of energy of the electron. Therefore, you still need to draw the excited state, even though it's like no changes. Okay, there is actually changes. Alright, we just can't see it because the arrangement of the electron is the same. So the arrangement of the electron is the same in your excited state for nitrogen in ammonia. There will be no changes at this moment. Alright? The pair electron has nowhere to go because there is no d orbital and the p orbital is already full with the single unpaired electron. So there's nowhere to go. So we remain your 2s2 over here. Alright? Well, for the nitrogen hybrid state, what would happen to the hybrid state? As always, looking at the hybridization that you have determined, which is sp3. So we need 1 box from the S and 3 boxes from the P. So we need 1 from the S and 3 from the P. And the new hybridized orbital form is your sp3. Look at the number of electron. The number of electron cannot change. In the s orbital, we have 2. So you shall have 2. In the p orbital, you have 1 each. So you will have 1 each. And you cannot change this. Okay? And once you're looking at your sp3 hybridized orbital, you realize that you have a pair electron. And the pair electron is your lone pair. The single electron is your sigma bond. Can you see your lone pair in your Lewis structure? And the 3 sigma bond with the hydrogen. And that is how we show the presence of lone pair in your hybridization process. Simple? Easy. We shall then end with the ground state of your terminal atom, where your terminal atom for this structure is hydrogen, and the ground state of it will be 1s1. And that is our hybridization process of your ammonia. So slightly different is this lone pair. So whenever you have lone pair must be in the hybridized orbital. And how can we show the presence of lone pair in the hybridized orbital? The electron must be paired up already. That is what we call lone pair. Make sense? Simple. From that, let's go for your orbital overlapping. So let's go for your orbital overlapping of your ammonia. Just a kind reminder of your Lewis structure. The Lewis structure of ammonia looks something like this. Knowing that it's a sp3 with tetrahedral. Okay, this is what we have done in the previous slide. Alright, so for the orbital overlapping, we always start with the central atom. Your central atom is your sp3 hybridized orbital in the shape of tetrahedral. I hope you can draw better right now. And make sure you label them. That is my nitrogen, which is my sp3 hybridized orbital. Put that down. Make sure you draw and then you label. Okay? And next, since we are having lone pair, guys, make sure you position the lone pair first. And we have discussed about tetrahedral just now. If your tetrahedral having lone pair, the lone pair can be located in any one of the lobe. So let's say I put down my lone pair over here. a pair-up electron even without overlapping. Okay? So that is the position of my lone pair. Therefore, this orbital will not overlap with anything else. That is my lone pair. Make sense? Next, your nitrogen right now forming a sigma bond with hydrogen. Hydrogen valence electron is 1s1 located in the s orbital. So all the sp3 that left will then overlap with a s orbital that belong to hydrogen. And in this shared region, in this overlap region, is where you form a sigma bond. And the sigma bond is coming one electron from the sp3, one from the 1s of the hydrogen. So same thing, I will have another s orbital overlap with the sp3 hybridized orbital of my nitrogen. And in the overlap area, we will have a pair of electron with the opposite spin, which is your sigma bond. See that? Another one, and the last but not least of your sigma bond is between your sp3 hybridized orbital and the s orbital of the hydrogen. Bear that in mind, the overlap region is actually your covalent bond that have one electron from the nitrogen, one electron from the hydrogen, forming a sigma bond. And this is your orbital overlapping of your ammonia with the position of your lone pair correctly in the geometry. Make sense? Next, we have ClF3 over here. Let's start off with the Lewis structure first. So we are done all the way down to your geometry, from your Lewis structure to your electron domain, and then from the electron domain, we can work it out the hybridization, which is sp3d. From the hybridization, then we can know the geometry, which is trigonal bipyramidal. I hope you remember the trigonal bipyramidal looks something like this. Okay? But before we go for the orbital overlapping, let's proceed to your hybridization process first. Let's look at the position of your lone pair in your hybrid state. Okay? Starting off with the central atom chlorine, ground state. Knowing that the valence electron of your chlorine at ground state is located at 3s2 and also 3p5. And since we already identified the hybridization, which is a sp3d, therefore, obviously, we need the presence of d orbital. Therefore, we will be drawing your 3d, even though at this moment, your 3d right now is still empty. So we will have your 3d. So your chlorine ground state in this question will look something like that. And guys, looking at your central atom right now, how many lone pair we have? How many sigma bond do we have? Alright, so how many pair up electron that we need? How many single unpaired electron that we need? So obviously, we need 2 pair of electron. Agree? And we need 3 single electron for the sigma bond. See that? Okay, this is what we need in the excited state and also the hybrid state later on, according to your correct Lewis structure. Therefore, the chlorine excited state. Looking at your chlorine excited state over here, I need 2 pair up electron only. First pair, second pair. And that is the only pair electron that I need because I only have 2 lone pair. So what happened to this pair up electron? This pair up electron, we don't want it. We want to make it to become single unpaired electron. So how do we do that? We are going to excite this pair up electron, one of it into your 3D. Alright, we only excite one pair up electron into the 3D. These 2 will remain because they are lone pair. See that? Alright, so we do not need to excite everything. The number of electrons that you excite will depend on your Lewis structure. Therefore, your step 1 Lewis structure must be correct before you can proceed. Okay? From that, you already can know how many pair of electron I need, how many single unpaired electron you need. Okay? So, for this chlorine excited state, the one in your 3s shall remain. The one in your 3s remain unchanged. While for your 3p, some will remain unchanged, some will then being excited. The first pair electron in your 3p remain unchanged. The second pair will have one left. And then you have another single electron that is original single. And then your 3D right now having new friend. Your 3D orbital that was empty a moment ago, right now is no longer empty. We have one electron that's being excited from the 3p orbital. See that? And then we move to your chlorine hybrid state. So, and the hybridization that we are looking for is your sp3d. sp3d means we are taking 1 from the S, 3 from the P, and 1 from the D. So in your hybrid state, shall look something like this, which is your sp3d. 1 from the S, 3 from the P, and 1 from the D. And the 1 from the S having a pair of electron, the first box from the P having pair electron, and then the rest is a single unpaired electron. And don't forget, in the hybridization process, the number of orbitals must remain unchanged from the beginning to the end. Therefore, you have all this empty orbital. Make sure you draw it and make sure you label them. They are not involved in the hybridization and they don't have electron. Therefore, we call it as empty 3D orbital. Okay, that is your empty 3D orbital. And in this hybridized orbital, that is your lone pair, your 2 lone pair. Alright, that is your 3 sigma bond in the Lewis structure. Simple, alright? And of course, we are going to end it with the ground state of your terminal atom. And your terminal atom for this question is fluorine, knowing that the valence electron of fluorine is located in your 2p2 and your 2p5. So, your valence electron for your fluorine, 2s2, 2p5. So, this is the hybridization process of the ClF3 that having 2 lone pair and 3 sigma bond. Okay, simple, easy. Let's move to the orbital overlapping. Want to remind you, your ClF3 looks something like this just now. So, let's start off with our central atom, chlorine, that holding sp3 hybridized orbital in the shape of trigonal bipyramidal. Okay, label that is my sp3d. And this sp3d is for my chlorine. Okay, next, we are going to position the lone pair. As we all know, in the sp3d, the lone pair will be positioned in this trigonal. So the 2 lone pair will be located over here. Alright, the 2 lone pair will be located over here to achieve your T shape. Remember your T shape? Alright, we are going to achieve your T shape over here. So please make sure the position of your lone pair is correct before you move on. Next, we are going to do the orbital overlapping between your sp3d and also your fluorine. Your fluorine obviously is a 2p orbital just now. So drawing the p orbital of your fluorine. Knowing that is my 2p of the fluorine. Okay, it's an end-to-end overlapping. Make sure they are aligned. So in this overlapping area, that is my sigma bond. Agree? Same thing. We have another sigma bond between sp3d and also another 2p orbital of fluorine, forming the second sigma bond over here. Last but not least, the third sigma bond between another 2p orbital of fluorine. that is the 2p orbital of my fluorine, forming the last sigma bond that you have in this structure. So this is my ClF3. Okay, so I hope this is clear enough for you to show the position of your lone pair. Your position of your lone pair must be correctly placed, okay, according to the Vesper theory that you learned in your 4.2. Okay, there's one video talking about the Vesper theory and the central atom that having lone pair. That is the video that you can check out. And then when you position the lone pair correctly, you then can draw the orbital overlapping as always with the terminal atom. Make sure you draw and make sure you label everything correctly. Okay? And that is about orbital overlapping when you have central atom that holding lone pair. Next example, and also the last example for this video, IF4 minus. Okay? So let's go for some charge, starting off with your valence electron all the way to your geometry. So, as always, we are done with your Lewis structure as the first step, electron domain on the second step, that having 4 sigma and 2 lone pair. 4 sigma and 2 lone pair give rise to a 6 electron domain. When your electron domain is 6, your hybridization will be sp3d2. Okay? And the geometry is octahedral. I hope you remember how your octahedral look like. That is how your octahedral look like, roughly. Okay? Next, moving to your hybridization process of this. Before we go for the hybridization process, let's take a deep look into your Lewis structure. Your Lewis structure having 4 sigma bond and 2 lone pair. So in here, I have 2 lone pair and 4 sigma bond. So what do you think the hybridization process will look like? Let's see. So as always, we will start off with the iodine ground state, where the valence electron of iodine is located in 5s2, 5p5. And obviously, we need a d orbital even though at this moment is empty. And we need 2 lone pair, 4 sigma bond. 2 lone pair and 4 sigma bond means what? 2 lone pair means we need to have 2 pair of electron. 4 sigma bond means we need to have 4 single electron. Agree? 2 lone pair, 4 sigma bond. But looking at your ground state of your iodine, so if that is my lone pair, that is my lone pair, I excite 1 electron, I only have 3 single electron. But I need 4 single electron. So what happened? Because it's a IF4 minus. Looking at your IF4 minus over here means your iodine in this question is not an I neutral. Your iodine in this question is a I minus. In the other words, we need another ground state of your I minus. Your I minus over here will be the I minus ground state still. But what makes your iodine neutral and your iodine minus difference? 1 more extra electron. So, from the 5s2 just now, we still have 5s2, but your 5p is no longer 5p5. Your 5p over here will be 5p6. You will have this 1 extra electron because it's a negative. Why is a negative over here? Alright, it's a I4 minus. It's a negative charge over there. And the negative charge is actually coming from the iodine with extra 1 electron. Okay? And the 5D will still remain unchanged because there will still be no electron in the 5D even though right now it's a I minus. Just stay there first. So, the example of this question is the hybridization right now having extra 1 more step. Alright, the hybridization right now having extra one more step is for the central atom when you are holding charge. Alright, so you have your I minus with extra 1 electron, and to move to your excited state, we will then need to excite how many electron? I need 2 lone pair, so that is my 2 lone pair. So I will have another 2 electron that I can excite. So the first electron I can excite into 5D, the second electron I can excite into another 5D. Then you will have your 4 single unpaired electron. So right now it's no longer I, it's an I minus excited state. With the I minus excited state, your 5s that holding the pair electron will remain unchanged because that is my first lone pair. Your 5p over here, the first box will also remain unchanged having a pair of electron that is our second lone pair. And then in the second box of your 5p, the second orbital, will change to single unpaired electron. Another box will also change to single unpaired electron. While in the 5D that was empty just now, right now your 5D will no longer be empty. Your 5D will be having extra 2 single electron that are excited from your 5P. See that? That is your hybridization process so far. And for the hybrid state, I think that is quite easy when you have gone through the ground state and your excited state. Your hybrid state for the I minus will be pretty simple. As we all know, the hybridization that we want, sp3d2. So taking 1 from the S, 3 from the P, and 2 from the D. That is the hybridization that we want for the I minus. So your hybridization should look something like this. So that is my sp3d2. And first box from the 5s having a pair of electron. Second box from the 5p having a pair of electron. And the remaining will be your single unpaired electron. And must remember, the number of orbitals shall remain the same. Therefore, your empty 5d orbital still be there. 3 empty 5d orbital. So that is my empty 5d orbital. And what is that? That is my lone pair. Lone pair. That is my sigma of my central atom. Simple. Easy. Okay, very easy. And of course, the hybridization process will end with your fluorine terminal atom ground state. So the ground state of the fluorine, we have repeated so many times, that located in your 2s2 and also 2p5. And that is our hybridization process of your I4 minus. I think the main difference from all the examples previously is your I ground state having twice of it because we are changing from the neutral I to your I minus. So bear that in mind, whenever it's a minus, you need to check your central atom. Okay? So if it's a minus, then we will add in electron compared to your neutral atom because it's a negative charge. So you need to have extra electron. And when you have the ground state correct, the rest of the thing will be as follows. Okay? Alright, as simple as that, the hybridization process for your central atom that holding lone pair and also charge. Both of it. Okay? So next, let's go for the orbital overlapping of your IF4 minus. As always, guys, we start off with our central atom. Your central atom I over here having an octahedral shape with the hybridized orbital of sp3d2. So let's draw the central atom. That is my sp3d2, sp3d2, sp3d2. Label every single orbital that you have drawn. And that is for my iodine. And as always, position the lone pair. And in the octahedral, the 2 lone pair must be in the opposite direction. So let's say I put in the 2 lone pair over here in the opposite direction. Okay, make sure the lone pair is opposite each other. Okay, when you have the lone pair down, and then you draw for the sigma bond. And the sigma bond between your central atom iodine and your fluorine, obviously, is using your 2p orbital. So drawing the p orbital. Overlapping end to end to form a sigma. So make sure that is my 2p of my fluorine. And in this overlap area, you have your 2 electron, which is in opposite direction. That is my sigma. And since it's a sigma, make sure it's an end-to-end overlapping. Make sure they are 180 degree end-to-end overlapping. Okay? And we are going to repeat for the rest of the orbital overlapping, because everything is the same overlap with the 2p of the F terminal atom. And make sure you remember the charge. The charge of this is an IF4-, so it will be only completed when you put down the charge together. Alright? So that is the orbital overlapping of your IF4- with 2 lone pair and 4 sigma bond. Make sure you draw the geometry correctly of your central atom. Position your lone pair correctly. Then only you draw the overlap with the terminal atom. So when you draw the overlap with the terminal atom, what do you make sure is it's an end-to-end overlapping for a formation of sigma bond. So make sure it's all a straight line. So make sure everything over here is a straight line. So you form a sigma bond. Okay? And make sure you label everything as always. And this is the better drawing of your IF4-. Make sure the charge and the lone pair, everything is there, including the label of each and every of the orbital. And that's it for this video about the hybridization process and also the orbital overlapping for your central atom that holding lone pair, and also for the ionic compound when you have a charge. And I really hope that this video able to help you to understand about the hybridization process and orbital overlapping when your central atom having lone pair. If you have any question or any compound that I can help you with, drop it in the comment below and I'll get back to you as soon as I can. Remember to subscribe my channel, like the video and share it with your friend. I'll see you in the next video and thank you for watching.